So in the paper, I think it just recently published this 2016, January 2016, the Journal of Number Theory, kind of described in a real explicit sense. We described really explicitly the sort of new spectral correspondences between spaces of mass forms on the unit group of a Quaternion algebra, and this is something that I will identify with what you just did, and spaces of mass forms on a really nicely related congruent subgroup of the modular group. Ouch, did I lose my connection? So the congruent subgroups of the modular group. And this work is joint with Stefan Mural. He's at the University of Gothenburg in Sweden. And I sort of added just a little question here. Why is n gamma 012 new lambda of cocompact type? In some sense, because that's the question that has motivated what we've done. As Johannes mentioned, sort of, I'm from Medgar College, and Medgar College is a small, predominantly sort of black college in the City University of New York, and I always like, whenever I get a chance to speak any place, I always like to have a slide that says, I'm from Medgar College, and this is who we are. So, I started teaching here in fall semester of 1983. This college was established in 1969. It's named for the kind of famed civil rights person, Medgar Evers. It's in central Brooklyn. It's a senior college in the City University of New York, and really kind of what we try to do is to really do some real meaningful research within that context. As much as it's a real challenge, I mean, we really try to do some interesting work there. And so here's the sort of plan that I have. Sort of some basic ideas, and I actually put these ideas in yesterday, or maybe earlier today. So some basic ideas, and I really wanted to say something about the motivating historical ideas, and then to kind of broadly say, what did we prove in this paper, and kind of an outline of the proof, and then some speculation. But I strongly doubt that I will get through all of this. But I do think an outline of the basic ideas are certainly in order. And so this will be stuff so give me a sense. So I'm going to say this twice. I'm going to first say, kind of, here are the objects that are involved in the talk. And then I'll give some kind of history about where these objects emerge from, and then I'll try to say something about the proof. So what emerged in the talk earlier, and this is the part that I put in. So essentially what we're going to be dealing with, and this emerged in Quinn's talk, sort of arithmetic Fuchsian groups, discrete subgroups of PSL2R. So there are essentially just two main types of these arithmetic Fuchsian groups, subgroups of PSL2Z and groups of Quaternion type. And groups of Quaternion type, this was sort of mentioned before, are cocompact, so it means that they have compact quotient plates. And a typical example of such a group is the kind of group that you were just describing, that's sort of here. The congruent subgroups of the modular group, I mean, these are the most common examples. And the particular ones which I'm going to be working with are the gamma 0 n's. These are the so-called Hecke congruence groups. And so those are the objects. You just mentioned this, these subgroups of PSL2Z are cofinite, they have finite volume, and they have a finite number of parabolic fixed points. So I'll skip the bit about gamma 0 n, there's a subgroup of index in, and so on. Important from the perspective is kind of bringing some real perspective to what has been said. There's a notion of a Quaternion algebra, right? So these Quaternion algebras are central simple algebras of dimension 4 over some ground field F. And there's a structure theorem from Medgar which says, on simple algebras, which says that a Quaternion algebra is either a matrix algebra or a division algebra. And when the characteristic of the ground field is not 2, then we can always find these elements 1, I, J, and K for A over F, such that I squared is alpha, J squared is beta, IJ and minus Ji, where alpha, beta are one of the non-zero elements in the field. You know, in this context, in this context, a sort of familiar Hamilton's quaternion H is just the one that's isomorphic to -1 over R. Right? Yes. So, you know, the fundamental example of a quaternion algebra over a field is matrix algebra, and then we can make this really explicit by embedding into M2F adjoined with the square root of alpha by making the associated kind of identifications. Questions that arose, and I do this because I recognize, so, you know, you can look at they arose in both of the talks that preceded mine. Some of the quaternion algebras over familiar fields, so, you know, if you have a field F and it's algebraically closed, we know if all of the roots of the polynomials, then if something is algebraically closed, then all sort of quaternion algebras over are precisely matrix algebras. So for example, if you look at algebras over the complex numbers, then this is essentially sort of a matrix algebra. The real numbers are up to isomorphism. There are only 2 quaternion algebras over R, and so this corresponds to the case where both alpha and beta are negative, and then the other situation where alpha and beta, and that corresponds to the matrix algebra. In this case, we give the language that the algebra is split. But a rational field is kind of a bit more interesting. There are infinitely many non-isomorphic quaternion algebras over Q. Algebraic number fields, again, what was just described. Finite extensions of Q, for example, Q joined with the square root of 2. There are, once again, infinitely many non-isomorphic quaternion algebras over an algebraic number field. We can think of p-adic fields, where P is a prime, and completion of field Q with respect to the p-adic absolute value on Q. And for each prime, there is up to isomorphism exactly 2 quaternion algebras over QP, and that is either a matrix algebra or a division algebra. So the objects are quite rich. And so here is the basic outline of, you know, so if you remember anything about my talk, this is kind of what you should remember. You have a quaternion algebra over a field F. This is a central simple algebra of dimension 4 over F. You have this object O, which is an order that was described in the previous talk. This order has attached to it an integer called its discriminant, and so this discriminant is D. And so what I'm doing essentially is starting with this algebra and grabbing from it an order, and there are many kinds of orders, and there's an entire theory about orders. I'm taking a unit group in the order. This was also described in the previous talk, and associating to that unit group the Hecke congruence group gamma 0D, which comes from the discriminant of the order. So in some very nice way, from the quaternion algebra, what I get are 2 arithmetic Fuchsian groups. I get an arithmetic Fuchsian group O1, which is just a unit group in the order O, and I get a Hecke congruence group, gamma 0D, where D is the discriminant of the order O. And so what I want, and this was a question that I asked you, was what I want to look at now are the surfaces that come from these 2 Fuchsian groups that are derived from this quaternion algebra. And now what I want to do is I want to look at the space of L2 functions on this surface. So to the question that you just noted was that, you know, this is going to be something that is cocompact, and this one is going to be non-cocompact but cofinite, so it will have finite volume. And so in some sense, these are kind of, in their character, radically different kinds of surfaces. And so the next step is I'm going to want to look at the Laplacian and a space of L2 functions. And among this space of L2 functions are those things that we call mass forms. And so what I want to do is to sort of look at the correspondences between the space of mass forms on the cocompact group and the space of mass forms on the non-cocompact but cofinite group. And the Jacquet-Langlands correspondence sort of says that there is a correspondence between these two things. And it says this at the sort of adelic level, and you can't sort of say explicitly which group corresponds to which one here. And so essentially the work that we've done is to use the Selberg trace formula to be able to make very explicit the correspondences between very specific groups that come from very particular Quaternion algebras over Q to make this association. And that's the essential sort of broad kind of description of what we've done. Now I'll say, I'll say some more specifics. Right? So I suppose if you think of this as a kind of story, this association between the space of mass forms on the cocompact group, which comes from the Quaternion algebra, and the space of mass forms on the non-cocompact but cofinite group, which is also coming from the Quaternion algebra, then some way is implicated the sort of arithmetic of Quaternion algebras with the associate geometry of the surfaces that are sitting below. And this is the essential game that we're playing. So, but see, at every stage, these things are very complicated. As the talk, I mean, I'm simplifying excessively, but as the talk before pointed out, the Quaternion algebras themselves are complicated. The orders in the Quaternion algebras that you were computing are complicated. Right? So when you are interested in the sort of cocompact arithmetic Fuchsian groups, you're interested in the fundamental domains. So I was sort of extremely when I listened to your talk, I said, that was just too hard, right? Because even just trying to do it at this level is extremely difficult, right? So if you look at the cocompact Fuchsian groups and you try to really analyze them, the Hecke congruence groups, and then the spaces of mass forms on the respective, and then you have this kind of thing which attempts to tie them together, the Selberg trace formula. It's a pretty complicated set of things to work with. So that's the basic picture. Now to some specifics. So how am I doing? Okay, very well. So I'll be able to give you some specifics, and then I'll be able to kind of say. So the work that we've done sort of comes from a particular paper. It's called asymptotic densities of mass newforms, and essentially sort of lays out what I just laid out. So I have gamma, a cofinite arithmetic Fuchsian group. And so there are two possibilities: either gamma is cocompact or it's not cocompact. And then I have delta gamma, sort of the automorphic Laplacian related to gamma. And then I have this thing called the spectral counting function. So sort of n gamma lambda, which counts the number of lambda in the spectrum less than lambda. Actually, it should say here the discrete spectrum. Well, let me pause for a moment. Let me pause for a moment on that. It should perhaps say the discrete spectrum. So what Riesager noted in the paper was the following, and there are many again very interesting things here. Yeah, what he noticed was that the spectral counting function on the cocompact group had the following form. It was a sort of volume of O1/h over 4 pi times some lambda, plus an error term that was of the order of the square root of lambda over log lambda. And the spectral counting function for the non-cocompact but cofinite group had an asymptotic expansion of the form very similar. So in first, actually there should be a little constant there, very similar in terms of on the first term, but then something of the order of the square root of lambda log lambda. So the thing I want you to note is kind of like note on the the difference in the error terms on the cocompact and non-cocompact setting. And so then what Riesager did was he looked at a spectral counting function for newforms on the cocompact. So you might ask, well, what do I mean by newforms? So just imagine that I have a group and I have a subgroup, and there are forms on the group, and these forms on the group descend to the subgroup. But then there are forms that are on the subgroup that are intrinsic to the subgroup themselves. And so those, I don't count the ones that descend, but I only count the ones that are intrinsic to the subgroup. And so those are called newforms. And so Riesager figured out how to count the newforms. And what he did was he found that when he counted these newforms, what he found was that when D was a product of an even number of different primes, here's where the number theory starts kicking, what he found was that the newform spectral counting function had an asymptotic expansion that had an error term that was precisely like the cocompact ones. So see, in the case of the cocompact, the error term is of the order of the square root of lambda over log lambda. When he counted the newforms for particular values D, where D was a sort of product of an even number of different primes, what he found was that this behaved in some way as if it were coming from some particular, were associated with some kind of cocompact group. And so then the question for us, and this was the question that we worked on, was how do you explain this? And then to figure out sort of whether or not there were other values for D for which the spectral counting functions for Maass newforms had this particular form, they had this sort of cocompact form. And so what Riesager sort of what Riesager proved was that if you start with say M and T natural numbers, define n square free M n T squared, then the spectral counting function for Maass newforms on gamma 0 n is cocompact if and only if the following thing holds: n contains at least 2 primes, and n is a prime, and 4 exactly divides M. So you can see the case that I'm looking at, sort of gamma 012 is one of those examples, right? And so the question for us was, are there spectral correspondences which explain this theorem? And so we answer broadly yes. I kind of alluded to this at the beginning. How do you explain this correspondence? So correspondences between spaces of automorphic forms for cocompact and non-cocompact arithmetic Fuchsian groups are kind of twinned by something called the Jacquet-Langlands correspondence, which asserts that to any non-constant eigenfunction of Laplacian on a cocompact arithmetic Fuchsian group, there corresponds a kind of non-trivial cusp form with the same eigenvalue on some non-cocompact but cofinite arithmetic Fuchsian group. And so what we've been able to do, so I'll just say what we've been able to do is to explicitly identify particular orders in Quaternion algebras that correspond to particular Hecke congruence groups that explain these correspondences that Riesager noted in his paper some years ago. So I suppose it's a good place to pause. I mean, I had many other sort of things that I wanted to say, but I realized yesterday that 20 minutes is a very short time for a talk, and so I kind of reconfigured what I wanted to say. But broadly, I'll just quickly. So just one. Yeah. Just no. This is entirely different. Just as a you might be asking, like, what does a Maass waveform look like? And if you look at this is an example of a picture of a Maass waveform, and you might say, well, why does that look familiar to me? And you can start thinking, hey, it looks familiar because I've seen this picture before. This picture looks like the picture that folks have when they do the Chladni plates. Do you remember when you vibrate plates and you see the dust form? So in some ways, these are examples of a kind of a mathematical, the sort of Maass forms are a kind of mathematical realization of this thing that physicists kind of already know and work with. And I just want to, and so I was going to describe things about the spectrum and so on. And so I just wanted to sort of broadly end with kind of, you know, what we've been able to do, which is we've been able to kind of establish kind of particular correspondences, not only between, say, the cocompact group and the Hecke congruence group, but also between particular kinds of orders that once they have some particular numerical, so for example, in this case, just loosely, so if I look at the newforms, so imagine that somehow there is some kind of discriminant, say 30, and so 6 times 5, 10 times 3, and 15 times 2, and you can see what you see here is, like, for example, 6 would be, you know, I'd have 2 primes, 2 and 3, and then 5, and then 10, I'd have 2 and 5, and then 3, and 15, I'd have 3 and 5, and then 2. So there's a mechanism by which not only do I have correspondences between cocompact and non-cocompact, but I've also been able to establish that there are correspondences between different cocompact ones that come from Quaternion algebras. So I'll pause here and thank you very much for listening.
Does anybody have any questions for Terrence? Questions? Yes.
Yeah, there's like part of what you said I understand a lot that I don't understand. But I know that one way of sort of classifying these Quaternion algebras is using the ramification set. Have you thought about like how that might relate to the geometric phenomena?
No, we haven't. But the ramifications play some role in what we do. Yeah.
Any other questions? Well, let's thank Terrence.
Thank you.
I wish we could have heard more. I mean, it looked really. I mean, it was getting.